So welcome to the Plane Curves class today. So that's like a complete COVID lecture today. It's completely empty here, but I'll give the class nevertheless. So last time we considered elliptic curves as an example of the theory and the results that we had before. And today, or in the last 2 weeks, there's another more theoretical result, which is one of the most important results about plane curves or curves in general, actually, and which also gives another algebraic motivation for the term of a genus of a curve that we had already seen in the complex case, where for a complex curve we had like topologically the number of holes in the curve, and that we interpret it as the genus. Oh, there are people coming, that's great. So so what we do today, this result that I talked about is in the last chapter. It's the so-called Riemann-Roch theorem. And let me start maybe with the motivation. So the idea here is the question about how many rational curves there are on a projective curve in a sense. So the motivation or idea in general is we start with F(a) as usual, well, in the last chapters here, a projective smooth curve over an algebraically closed field. And informally speaking, the question is about how many rational functions are there on F. And this how many is to be a bit put in quotes, because the question is, how can we make sense of this question? So there's two extremes, I guess, that we know already. First of all, if we restrict even to regular functions, then we had seen that on a projective curve, the only regular functions are constant. So if we restrict to regular functions, then the result is sort of boring because we get only constants. Whereas if we allow all rational functions, then we can take essentially all possible quotients of two polynomials, and there's just infinitely many choices. So it would be in whatever structure. It's like a ring, it's a field of rational functions. It's an infinite dimensional vector space. There's also not much structure in there. So if we have arbitrary rational functions, then we have a huge number of such rational functions. So, say, for example, there's an infinite dimensional space of such rational functions. Which also doesn't have a useful structure. So the interesting question would be somewhere in between. So that means have functions that are not just regular, so they may be allowed to have poles, but in a somewhat restricted fashion. So not arbitrary poles of arbitrary order at any point. So the actually interesting question is somewhere in between. And that will be about the following spaces that we want to construct now. So we need something in between regular functions and arbitrary rational functions. And that is about the following construction, about the spaces that were actually also given on the last homework set in the last question, so question 4 on sheet 6, where I had copied the definition because it's only in class today. So for that, we first let F be a projective curve as above and as always in this chapter, so smooth and over an algebraically closed field as usual. And we pick a divisor D in div F, so it's an actual divisor, not just a divisor class. And we set it's sort of a standard notation even. So there's a capital L of D, and that is the following space. It is the set of all rational functions, so kf star, say without 0 first, with the property that the divisor of phi plus the given divisor d is effective, so it's greater or equal to 0. And to make this into a nice space, then we will see that it's a vector space. Actually, we have to add the 0 function here. We'll take this together with a 0. So that's the definition first. And let's just, in this construction, have a look at this space, what we can say about this. So maybe let's first check what this condition actually means. So this is a condition that a divisor is effective, meaning that the coefficient of this, whatever that means, okay, which means that the coefficient of each point in this divisor is non-negative. So what this here means is, i.e., if, say, the divisor we write as a sum over all points, it was an f, and then the coefficient, we call this AP times P, so AP is just the coefficient of the point P in the divisor, then what this condition means is that we have greater or equal to 0 at every point. So that means at the point P, the coefficient here is the multiplicity at the point P of phi, and then plus this AP is greater or equal to 0 for all points. Which, of course, we can rewrite as that is equivalent to saying that the multiplicity mu P of phi is greater or equal to minus AP for all P. So that is exactly the condition here. And so it's a condition at every point, and if we translate this into the standard notions of zeros and poles, that means, so this AP will be at most points, it will just be 0. So a divisor is always a finite sum, so most AP are 0. At this point, this just means that we have a regular function, so it's a function that is not allowed to have any poles there. However, if there is a point P that has a positive coefficient here, so where AP is some positive number, then this means that the multiplicity may be at least the negative of this positive number. So that means we might have a pole of that order at the point. So i.e., phi may have a pole of order at most AP if AP is greater than 0. If AP is less than 0, then this number here would be positive, and this means that the order here must be at least this positive number. So that means that we must have a 0 of at least that order. So phi must have a 0 of order at least minus AP if AP is less than 0. And at all the points where AP is 0, which is at most points, there's essentially no condition. The function is just regular, has no poles. So phi is regular at all other P. And so this condition here is for this union of condition we have for all points P and M. So essentially we consider functions with prescribed zeros and poles. And the way they are described is encoded in that divisor. So that's the condition that we have here. The reason why we have this pole of order at most and here 0 of order at least is that this makes the space have a nice structure. Namely, this is actually a vector space. So note that L of D is a vector space over K, and that's easily checked. So if we have two elements, so say if phi and psi are in this L of D, i.e. we have in this condition written above there, so mu P of phi is greater or equal to minus AP, and mu P of psi is greater or equal to minus AP, then if we form the sum, so the multiplicity of phi plus psi we had seen is at least the minimum of the two numbers. And as these numbers are both AP, minus AP, this means this is greater or equal to minus AP as well. And if we have mu p of some lambda times phi, where lambda is an element of the ground field, then, well, either it's zero, then we get the zero function, which is included there as well. And if it's non-zero, then the multiplicity is even fixed because it's additive, and this would be mu p of lambda plus mu p of phi, and mu p of a constant is just zero. But it means this would be the same actually as mu p of phi, at least if lambda is not zero. And that is again then greater or equal to minus AP. So this will give a sub-vector space of the space of all rational functions. And that means in particular that we can consider its dimension. And that dimension is usually denoted by the number little l of d. So that's how that is defined. And that is a useful question, what this number is. So what is the dimension of that vector space? In that sense, how many rational functions are there with prescribed zeros and poles? So I might have a curve and say, so I might allow a pole of order 1 here and a pole of order at most 2 here. How many rational functions are there that satisfy that? Always set little l of d to be the dimension of this capital L of d, and the goal is compute this number. Well, the question is, what is this number? So that would depend then on the divisor, so on the given zeros and poles. And the question is, what's this number? So first of all, I mean, it's not even clear, of course, that this number is finite. So you might write this as an element of the natural numbers union infinity. But in fact, we'll see that these are all finite dimensional vector spaces, so that the results to this question that we get here are actually nice numbers. Yeah, so that is, in a sense, the main object of this chapter. So compute these numbers L of d, and then that answers the question how many rational functions we have of certain type. And we just want to start like with easy cases and easy lemmas and then build this up, and then at the end have actually quite a strong theorem that tells us what the number is in most cases, and it's much more subtle than one might think at the beginning. So let's start with some very simple examples. Namely, what we could always do is take the zero divisor. So if we take d equals 0, then this means the condition is essentially that the function is regular everywhere. So it might have no poles, must be regular, no condition on zeros. And that's exactly those constants up there. So that means we have a one-dimensional vector space. So for d equals 0, so L of 0, capital L of 0, is isomorphic to k. These are just constant functions. And hence, we get little l of 0 is just 1. So that would be the first simplest case. Also, a very simple case is that if the given divisor is of negative degree, then this is essentially not possible. So negative degree for the divisor means that we have many points with negative coefficients and maybe no points with positive ones, which means pretty much that we don't really allow poles, but we require many zeros. And well, if we are ready only for no poles, we have only the constant functions. If we additionally require zeros, it's not going to work out. So B, if the degree of the divisor is negative, then they claim that L of D is just the zero function, i.e. little l of d is then always 0. And the reason for that is simply, if we had a rational function inside there, so that means where div phi plus d is greater or equal to 0, and we run immediately into a contradiction. So if we had a non-zero rational function in kf star with div phi plus d greater or equal to 0, then by taking the degree of the equation, so that's a homomorphism, so I can split it onto the two parts, we get the degree of the divisor of phi plus the degree of d is greater or equal to 0. Well, the divisor of a rational function always has degree 0. So right, it has equally many zeros as poles, so this would be 0, and that's a contradiction, right? Or the other way around. formulated in a positive way. If you want to have any non-zero rational function in that space with div d plus d greater or equal to 0, we must have a non-negative degree of the divisor. As written down here, this is a contradiction. Dig d less than 0. So the interesting cases are clearly the one with a non-negative degree. So that doesn't mean that the divisor cannot contain any points with negative coefficients, so clearly not, but the total degree must be non-negative. So these are probably the first easiest examples, where one can see immediately what's happening and where there's not much interesting things going on. So to move on to more interesting cases, maybe let's also start with two remarks. And first of them is that these spaces L of D actually partially lie inside each other. Namely, if D is less than or equal to D prime, so that means the coefficient at any point is bigger in D prime, or at least as much as it is on D, then of course if something is LD, then it's also an LD prime, right? Because I just add more here and then the condition is still satisfied. So that means then L of D is just a subspace of L of D prime, which of course means that the dimension L of D is less than or equal than the dimension L of D prime. That I guess clear. And B is, as one might hope or expect, this space, or at least the number L of D, does not depend on the representative within its divisor class. So it means if I have two divisors which are linearly equivalent, then they would have the same number L of D. And the reason for that is the following. So if D is linearly equivalent to D prime, which means by definition that the difference, so say D minus D prime, is the divisor of a rational function, say psi, or some psi rational function, then one can write down an immediate isomorphism between L of D and L of D prime, which is essentially just given by multiplication with psi. So then we claim that the map L of D to L of D prime, which sends some phi to phi times psi, is an isomorphism. So it's the vector space isomorphism. So why is that? So that's just because the condition that we put on L of D, namely that div phi plus D is greater or equal to 0, is, I claim, equivalent to that the divisor of that plus D prime is equal to 0. I hope it is. So phi psi plus D prime is greater or equal to 0. So that's exactly the condition to be for phi to be in here. That is exactly the condition for phi psi to be in here. And that is just the same because this one here is the divisor of phi plus the divisor of psi plus D prime greater or equal to 0, and the divisor of psi plus D prime is just D. So that means these equations are exactly the same. And that means that this is an isomorphism, and in particular it means that the little L of D is the same as little L of D prime. So we can consider this little L of D as a well-defined function on the Picard group, so on divisor class. And little L of D is little L of D prime, i.e. this little L is well defined on Pig F. And so we will probably often use also little L of a divisor class. So that just works out as well. Yeah. Well, that's some very first remark, but that doesn't go very far in actually computing numbers. So that can be done mostly, in fact, by induction, in the sense that we pass from one divisor to another by just adding a point or subtracting a point. So we want to compare these numbers. I mean, either compare the spaces L of D with L of D plus or minus a point, and the same then with the numbers little l of D, little l of D plus or minus the point. So say as most arguments to compute either capital L of D or little l of D, D not P, are inductive, passing from a divisor D to D plus or minus P, and hence essentially yielding all divisors starting, for example, from the zero divisor, we need the following result. And we got the small lemma, and where this is actually useful already to compute some of these numbers. Namely, let F be a projective curve, and say we have a divisor on that. So D and div F. Then the statement in A is if we take then D plus a point P, so we just add a point to the divisor, then the number little l will go either stay the same or go up by 1. A is just a statement, so for any P on the curve, we have the number little l of D plus P is either the same as L of D or L of D then plus 1. So it might go up by 1, but it doesn't have to. And we'll see, in fact, later on that it really depends on the divisor on the point. So we might have, in some cases, we might have this case, and some we might have that case. So both can actually happen. So if we put this together already by induction, this means, of course, if we add a certain number, say n points, which might even be distinct, so needn't be the same, then of course we can go up any number between 0 and n, right? That's essentially induction. And we could write it in the following way. So for any divisor, say D prime, which is strictly greater than D at every point, so greater or equal to D, that means it's obtained by adding D prime minus D points. We have that L of D less than or equal to L of D prime is less than or equal to L of D plus the difference of the degrees, so plus degree of D prime minus D. So this B is essentially just induction from A. Right? So if we add 1 point, then either we stay the same or go up by 1. So B means if we add n points, where n is this degree of D prime minus D, then we can have anything in between. It stays the same and goes up by n. So the important thing is A, and B is just, I mean, as we will use it then later on, as we have already the induction in there. So how do we do that? In terms of inequalities, actually, one of them is already clear, right? Because we had remarked already up there, if one divisor is less than or equal to another, then the corresponding L spaces are subsets of each other. So by remark A up there, we clearly have that L of D is a subset of L of D plus P, and hence that the little L of D is less than or equal L of D plus P. Right? So that one bound is clear, so we cannot go down when passing from D to D plus P. And so the question is how to get the other bound, so which says that L of D plus P is at most L of D plus 1. And that is because we can write actually the subspace L of D as a kernel of a certain map. And that is the idea here is the following. So it remains to see that L of D plus P is less than or equal L of D plus 1, right? Because this is the other bound. And to see this, let's consider the following linear map of vector spaces, namely that starts with L of D plus P. And what it does informally is that we multiply it first with the suitable power of a local coordinate at the point, so that it's expected not to have any zeros or poles anymore. So which means, I mean, if we start with, say, D is the divisor, again, say AP is the coefficient. So for that, introduce some notation. Say let AP, as before, be the coefficient of P and D. And that means, of course, that AP plus 1 is then the coefficient of P and D plus P. And that would be then essentially the order of the pole allowed at most at this point. And consider now the linear map of vector spaces, where we start in L of D plus P and just go to the ground field K. So what we do is the following. So we map any phi inside there to, we multiply phi with a power of the local parameter, which we always call t. And the power is this AP plus 1. So AP plus 1. And then take the value of that at the point P. So let's check that this makes sense. What we have inside here is, so we know that the multiplicity of phi from UP of phi plus come from LD plus P, so plus AP plus 1 is greater or equal to 0. That just means it's in here. That's the condition at the point. AP plus 1 is the coefficient of P in the divisor, so that's exactly the condition that we are inside here. And so that means if now T here is a local parameter, which means it has order 1, then phi times T to the AP plus 1 just adds AP plus 1 to this order. And so this means that, well, that means that this inequality means here that mu P of phi times T to the AP plus 1 is greater or equal to 0. So that means it is regular at that point, and we can evaluate it and get a number. Right? So that's why this makes sense. And clearly it's a map of vector space. I mean, it's linear in phi, right? What we have in here. That is clearly a linear map. So what this informally does is, as I wanted to say this before actually, so one way of thinking about that is if you do it in the analytic setting, maybe as we did it last week, then we can we consider that C over C and have a complex manifold. Then we start with some meromorphic function, which might have a certain pole of some order. And what this does essentially is we consider this Laurent expansion of that function and look at the smallest coefficient. Right? So if we start with a T is the local parameter, so if the order is minus AP minus 1, then we start with a negative power maybe of T to the minus AP minus 1, and the coefficient in front of that would be this map. Yeah, so that is the map. And the point is now that the kernel of this map is exactly this L of D. And that is because note that the kernel of this map doesn't have a name, so it will be named, say capital phi. But the kernel of phi is just L of D, because kernel means that this has a 0, so that it maps to 0, and that this maps to 0 means exactly that the order here is not equal to 0 but greater than 0, so that we have a strict equality here, a strict inequality here, and that of course means that it's also in mu P of phi plus AP is also greater or equal to 0, and that means essentially we are in L of D. So phi of so capital phi of little phi equals 0 means exactly that this function here, so phi times t to the ap plus 1, has a 0 at p when we evaluate it. And that means we have a strict inequality here. So UP of phi plus AP is actually also greater or equal to 0 without the plus 1. And that, of course, means that phi is in L of D without the plus 1 here. So again, in the analytic setting, it means we start with functions having a certain Laurent expansion, starting with maybe negative power of t. And if we impose the condition that the initial coefficient is 0, then this means exactly that the Laurent expansion starts 1 power later. Right? Essentially what this says. Yeah, so that means the kernel of this map is just L of D. And by the homomorphism theorem, that means that the quotient of LD plus P modulo dP is isomorphic to the image, but the image is a subspace of K, so it has dimension 0 or 1. And that's exactly the statement here. So, so by the homomorphism theorem, we have that L of D plus P mod L of D, which is just L of D plus P modulo the kernel of phi, is isomorphic to the image of phi, and that is a subspace of K. And that means that the dimension of L of D plus P mod L of D is less than or equal to 1. That's exactly what we need. Right? So that means that the dimension L of D plus P is less than or equal to dimension L of D plus 1. That's that statement. So that's the reason why this is true. So that means, and that's why these inductive arguments often work quite well. So if we just add a point, then we cannot jump very much. We just either stay the same with L of D or go up with 1. And as I said already, part B is then just follows from A by induction. So this follows from A by induction on the points added to go from D prime to D, so by induction on the points in D prime minus D. Also D prime minus D, yeah. So that let's take a first statement here. A corollary is that we can compare this now. We can combine this to a divisor where we know that we must get 0, namely if the degree is negative, then we know that the number L of D is 0, and then add all the remaining points to go to an arbitrary divisor, and that gives us already an estimate how big this number L of D can be at most. Namely, whenever the degree is negative, we must have little L of D equal to 0, and then when it starts getting non-negative, the degree, so if the degree is 0, we can go up by at most 1, and then so on for each further degree. That means that we have an upper bound for this number little L of D, which is just the degree plus 1. So that already follows from that. And let me write this down as a corollary. So again, let F be a projective curve. And say we have a divisor on F. And say it's greater or equal to, with the degree non-negative. Otherwise, we already know it's 0. So if degree D is greater or equal to 0, then the statement is L of D is less than or equal to the degree D of D plus 1. And in particular, of course, that means, which we couldn't answer at the beginning, that this number is clearly always finite. So in particular, L of D is finite. And we have a clear bound on that number. So as I said, the proof is quite simple. We just compare it to a divisor where we know that we must get 0, namely pick, say, P any point on F. Set n equal the degree of D plus 1 and set D prime to be D minus NP. So it's a very naive way of doing that. So we have a divisor D that has a certain degree, D plus 1. We subtract more points than the degree is, so we get a divisor of with negative degree. So that means the degree of D prime is deg D minus n, and n is deg D plus 1. So that means that is minus 1. And in particular, that's less than 0. And that means that L of D prime is 0. But we obtain D from D prime by just adding n points. So that means the part B of the lemma up there gives us the estimate that we want. So hence by lemma B, we conclude here that I guess the role of D and D prime is swapped, right? So D prime is now the smaller divisor, so here it's the bigger divisor, but I guess that's okay. So we use the second inequality here, and we conclude that L of D is less than or equal to L of D prime plus the degree of the difference of the divisors. The difference is just n times P. And this is 0 here, and this is n. And n was, of course, the degree of D plus 1. Right, so that's a very simple just application of that. And in particular, that gives us an upper bound for this dimension of the space. Yeah. Any questions? Right, so yeah, as well. So let's consider a few examples and check whether we might have equality or strict inequality here. And for that, we start again with the easiest curves, namely of smallest degree. And start with curves of degree 1 and 2, where we had already seen, in fact, that any 2 points are linearly equivalent, meaning that the Picard group is just given by the integers, and so things should be easier here. So examples. A, which is so that f be a curve with of degree 1 or 2. So deg f equals 1 or deg f equals 2, where we had already seen that the Picard group of f is just the integers. So any 2 divisors of the same degree are linearly equivalent, and that means, as we've seen, it's already well defined on that, we can essentially pick any divisor of degree d to compute that number. That means any divisor of degree n is linearly equivalent to NP for any point P. In particular, that means that also it's pretty much the same statement that any 2 points are equivalent. So that means P minus Q is equivalent to 0. And in particular, P is linearly equivalent to Q for any PQ, which means that there is a rational function phi in K of F star such that the divisor of phi is P minus Q. Okay. And so what that means is if we consider the function, I guess I want q minus p, it's nicer here. So this function phi, that means it has a defies a pole of order 1 at p, a 0 of order 1 at q. And if we consider the kth power of that, so the phi of k is k times q minus k times p. So it means it has a pole of order exactly k at p and no other poles. I mean, it must have zeros at q, but we don't care about that. No other poles. And what that means is that this function of phi to the k is in L of AP, because that means these are functions that can have a pole of order at most k, so that's true. But it's not in L of k minus 1p, because here we allow a pole order of only a pole of order k minus 1, but we have a pole of order exactly k, so it's in here but not in there. What that means is, what this means is that in this chain, so if we have L in 0 contains L of p, 2p, and so on, and up to L of np, these inclusions are actually all strict, because we found a function for all k that sits in the space but not in the one before. This has all strict inclusions. And this L of 0 was just k, so there the dimension was 1. That means the dimension has to go up in each step, but we had seen that it can go up by at most 1. And so that means at the end we'll have an n plus 1, which is the degree plus 1. And so that means, in fact, for these curves of degree 1 and 2, we do have, in fact, equality. So there the L of b is always the degree of d plus 1. So we've checked it here for divisors of the type n times p, but these are all others are equivalent. And hence, for these curves, we've essentially completely solved the question. So this little L of b will always be deg d plus 1. So let me write all that down. So this means the little L of 0, which is 1, is strictly less than L of p, strictly less, and so on up to L of np, which means that L of np is at least n plus 1, which is the degree of np plus 1. But we have already seen the other direction. So this less than or equal always holds. We've just seen by the lemma. This means that L of np is equal to deg of np plus 1. And that contains all divisor classes, representative of all divisor classes. So if these are all divisor classes, we conclude that L of d is always deg d plus 1 for deg d greater or equal to 0 in this case, right? So for curves of degree 1 and 2, again, I mean, as we've seen it many, many times already, these curves of degree 1 and 2 are very simple. I mean, anything we try to do essentially becomes trivial quite soon. However, that's the case really only for those curves. So let's pass on to curves of higher degrees. So B now, let the degree of f be at least 3. And so the main feature we had seen then is that no 2 points are linearly equivalent on these curves. Right? So there we have P is not linear equivalent to Q for all P not equal to Q. So that was one of our main results here. And what that means is if we start maybe with just the same here with an L of P, I claim that in that case, we do have an equality here at the beginning. And the reason for that is that we do allow a simple pole at some point. But this means if we had a simple pole only at one point, we must also have exactly 1, 0 at some other point, because zeros and poles are always the same number. And so that means the divisor of such a function inside there must be q minus p. But there is no rational function of divisor q minus p unless p is equal to q, but then we have a constant function. This means that in fact L of P is K, and hence equal to L of 0, i.e. little L of P is 1, which is less than the number up there, so less than dec P plus 1. And so the reason is if we have a function in there, so if we had, so we know already L0 is contained in there. So it might be that there is a function in LP that is not in L0. So if we had some phi in L of P which is not in L0, then it must have a pole at the point P. And then phi must have a pole of order 1 at P and no other poles. And that means that the divisor of phi must be q minus p, as the degree of the divisor is 0. So we only have one negative point, so we only have one positive point. And but by the result up there, that means p is q, and hence we don't have a pole. So this means, well, actually we do have p equal to q, i.e. the phi doesn't have a pole. And that's a contradiction. So that means this is a first case that we see where also in this lemma up there, which probably is no longer there, where we said that L of D plus P is either the same as L of D or it's one more. So this is the first example where we see where it's actually the same. So if we compare L of 0 and L of 0 plus P, so L of 0 and L of P, here it's actually the same. So that might also happen. And so that's also a first example where for a divisor of non-negative degree, the result is not dec D plus 1. We can actually put this together with another thing, namely if we are still on a curve of degree at least 3, so again, that dec F be at least 3, so then I claim if we consider the divisor E minus Q for P not equal to Q on F, I claim that this is actually the 0 space, so there is no function in there at all. So why is that? So of course this is a subspace of L of P, as this divisor is strictly smaller than that one. But L of P was just the constants. We've just seen it in B, right? So that is also equal to L of 0, which is K, which is just constants. So these contains only constant functions, but they also must have the 0 at Q, so they must be the 0 function. Such a constant function in L of P minus Q must also have a 0 at q. That means it's the constant function phi. Say that means phi is just 0. And hence L of p minus q is 0, which means that the little L of p minus q is also 0. And what that means is, maybe I've said this already as a remark, so maybe in contrast to what one might think from such results here in the corollary, the number little l of d does not depend only on the degree. Right? For example, on a curve of degree at least 3, if we take L of 0 of the 0 divisor, we get 1, always get 1, it's a constant function. And here we have a divisor that also has degree 0, but there the result is 0. So that means we see already that this L of D, I mean, it does only depend on the divisor class, but it does not only depend on the degree. We really need to know where the points are on this in this divisor. Hence, as L of 0 is 1, and L of D, L of p minus q is 0, and both divisors here have 0, have degree 0, L of D does not only depend on the degree, as one might hope, as it's sort of a discrete invariant, and the position of the point is a continuous, is a moving thing. So if somehow a discrete number depends on a moving thing, one might expect it to be constant, but it's actually not. So it does not only depend on degree, but also on the precise position of the point in D. Well, in that sense, precise meaning, of course, here it doesn't matter what P and Q are, but if P and Q happen to be the same, then you get a different result. So it's not just a function of the degree. And that's why this question is a little more delicate than what one might hope, right? So it's not, you have to look deeper into what the points actually on the divisor are. So that means there is no hope that there is a formula that just computes L of D in terms of the degree. There's no formula. To compute L of D from deck D. And as I say, for an exact formula, this is what sort of Riemann-Roch does later on, but we do this next week. But there is at least an estimate in the other direction as well. However, we also we can find a bound by deck D also from below. So not just from above. So we had seen a bound from above, it's at most deck D plus 1. We can also bound it by the degree from the other side, and that works as follows. So that's a proposition and definition. So again, as before, let F be a smooth projective curve. Then the statement A, there is such a bound, namely there is a smallest constant that we can subtract from there, which will be a lower bound for all these L of D, no matter what the divisor is. So that's the statement A. There is a, well, I write here unique, although it's sort of trivial by the definition that it's unique. So there's the unique smallest number, natural number G in N, such that L of D is greater or equal to the degree of D plus 1 and now minus G, and that for all devices. For all the so yeah. So in fact, as I said, so the unique is sort of clear, right? I mean, if it's the smallest number such that it's the smallest natural number such that something holds, that is also always unique. So I'm just writing that because then we can give this a name. And this G is actually the algebraic version to define the genus of that curve. So we call the algebraic genus of F. So one example, we example, we need B for that. So what is this number? Maybe no surprise, it's the same number as the one we know. So B, and that's sort of the algebraic degree genus formula. Namely, we can say exactly what this G is. Namely, G is, as one might expect, D minus 1 choose 2. And that is precisely the number that we got from the topological genus. Right? When we considered complex curve and introduced that there was a topological number measuring how many holes this have as a topological space, there was exactly this number. And that's an analytic or topological way to introduce the genus. And this, of course, now is entirely algebraic, which in particular means you could do it over any field. You don't need the complex numbers for that. Any algebraically closed field would be okay. But the number is still the same. And that's the way how one could use it, how one could introduce that using entirely algebraic methods. So just as an example, maybe I have to write this down, but before we start with the proof, as we know that the number is the same as the one we knew before, then we know that a degree also follows from the formula. Like degree 1 and 2 means genus is 0. Right? So for degree 1 and 2, G is 0, and hence this means we have the other inequality without that shift, and that means we have equality. That's what we have just seen. And for degree 3, for example, if we have a cubic, then the genus was 1, and the number here is 3 choose 2, which is 2 choose 2, which is 1. And hence this L of D is at least deg D plus 1 minus 1, so deg D. So that means for degree 1, the number is always either deg D plus 1 or exactly 1 less. And for higher degree, like the possible difference between L of D and deg D plus 1 can get bigger. So here in that case, we had seen one case where the difference was exactly 1. Right? For the degree 0, we expect it to be 1, but we had an example where it's 0, so it's off by 1. And that's for a cubic curve, all that can happen. So that statement here that we have up there usually goes under the name Riemann's theorem. So so there will be a theorem called Riemann-Roch at the end, and this is sort of Riemann's part of that. Or sometimes it is called Riemann's theorem. In fact, we'll prove pretty much both at the same time, but the statement that there is such a bound from below where you just subtract a constant which is universal for the curve is that statement here. Let's just prove that statement. So the goal for that is so for that, we had already part of it actually on the current exercise sheet, on the sheet 4. And namely, what we know from that is if we set, so let's do it like follows. So let's say we set d equal to that number, d minus 1 choose 2. Then we actually saw on the current homework by a sort of simple computation, I would say, with some exact sequence computation, that there are divisors, one can write down explicitly divisors, for which we do have an equality here. Namely, if we pick for d just the multiple of a line. By homework, that is 6, 4. We know that for d equals the divisor of, so there I wrote z to the n, which is the same as n times the divisor of z, so z just the last coordinate on the curve. We do have an equality here. So in the exercise, the statement then is just for this divisor n times div z, that L of d is equal to deg d plus 1 minus this number, d minus 1 choose 2. That's exactly what we have in the question in this homework problem. We know that for this divisor, we have equality. And that is for n at least d. In a star, at least a star. And so if there is a bound like that, this is the best possible bound, this number, because there is a divisor such that it's actually obtained. And so that means the only thing that remains to be shown is that for all divisors, actually, we do have this inequality. And because then, as there is a divisor where equality holds, this is the smallest possible number that can do it. Hence, it suffices. So that the inequality n star holds for all divisors. And because there is no way to subtract more, because for some divisors we do have equality. And now we can do in the following way. So let's first have two remarks, how this inequality changes when you pass from one divisor to another. So to do this, note first the following. So two remarks before. First of all, that's quite an obvious remark, that we can pass from the divisor to any linearly equivalent divisor without changing anything in the inequality, because L of d doesn't depend on that and the degree doesn't depend on that. So let's put first for any divisor d and this f. So if the inequality star holds for d, then it holds for any d prime which is linearly equivalent to d, right? Because both sides don't change. Second statement is, again, if the star holds for any divisor, then I claim it holds for any d prime which is less than or equal to d. So I can subtract points and that won't go bad. And the reason for that, I mean, just intuitively, we can just write it down in a minute, but intuitive reason is if we subtract a point from d, then this side always goes down by 1, right? Because the degree gets 1 less. And this might go down by 1. Right? And that means that the inequality that way is still true. But we can also write this down more precisely. That's exactly this inductive argument that we had before. So say, assuming that L of D is at least deg D plus D minus G. So assuming the inequality for D, so that means L of D is at least deg D plus 1 minus G, and what do we have? D prime is less than or equal to D. That means by our lemma that we had that we can express, I think we've written it down the other way around. So L of D was bounded from above by L of D prime plus the difference of the degrees, so deg D prime, D minus D prime. That was just this adding a point, just raises this by 0 or 1. And if we just swap this around, so this means that L of D prime is greater or equal to L of D minus deg D minus D prime. And now L of D was assumed to be at least deg D plus 1 minus G. And here we have minus deg D plus deg D prime. And deg D just cancels, and we get deg D prime plus 1 minus G. And that means the inequality holds for D prime as well. But that's just the formal way of writing this down, what I just said. So if we just subtract the points, and this always goes down by 1, so this might stay the same or go down by 1, so the inequality. And these two statements together we can now use in the following way to obtain this for any divisor. Namely, we start, essentially we want to reduce that to the divisor where in the exercise on the homework sheet we showed that it is true. Namely, for z to the n, we know it's true. Actually, with equality, in particular, the inequality is true, and we want to reduce it to that. Using this, we can do the following steps for any divisor. D, div f. First of all, we'll split this into positive and negative points. We can write D is, say, P1 plus and so on plus Pn. So this is all the positive points contained in the divisor. And then we subtract some points. I write this as minus E, where E stands for any effective divisor. So essentially, this here contains all the positive points, meaning points with positive coefficients, and this contains all the points with negative coefficients where E is effective. And there's no assumption on the degree. So in particular, that like the degree of E might be bigger or smaller than that of N. It doesn't matter, right? But any divisor I can write in that form. So we have a couple of positive points, a couple of negative points. So what we do now is for each of these positive points, or first of all, I want to say, well, we can write it in that form, and namely because I want to reduce it to that case, with N at least D. So that N at least D was a requirement in that computation here. That's why I want to have this. And of course, we can always achieve that because there's no assumption here that the points in E might not coincide with the PI. So that means if we have fewer points in here, I just add the point a couple of times here and subtract it in E. Right? So it's no problem to make the degree of the positive and the negative points big, as some of them are allowed to cancel out. What we do now is find lines that have these pi as zeros. So that means we pick any line Li through pi for I from 1 to n. Now pick lines L1 up to Ln. with pi is on Li. Essentially, really, it doesn't matter, any line, and consider the divisor d prime, which is defined to be d plus, and then the divisor of z to the n over L1 times Ln. So we'll see in a minute why. But the first thing we can see is, so first of all, I mean, that does work, right? So z is a linear function, the lines are linear functions. So that's a quotient of homogeneous polynomials of the same degree. That's a rational function. And in particular, that means that d prime is equivalent to d, right? Because it's d plus the divisor of a rational function. So it will be a divisor that is equivalent to d. And in particular, that already means if we want to show this inequality for d, we can equally well prove it for d prime because it's the same. So why do we do it? So why exactly that? So what can we say then about the divisor of d prime? Well, the divisor of d prime is then the divisor of d, of course, plus the divisor of the numerator minus the number of the divisor of the denominator. Means that's n times z minus the sum over the divisors of the Li from 1 to n. And the divisor of these. And d is just the thing up there, right? So that is p1 up to pn, and then plus n times the divisor of z minus, I think I got as well the minus e. So that is d. And now we have plus n times the z. And then minus the sum I equals 1 to n. Now the lines pass through the point, and that means the divisors of L clearly contain the point pi. So it means the divisor of Li is clearly greater or equal to pi. That's the only thing we need from these lines. They contain the point pi, so they will contain the point pi at least once. And that I want to use here. So pi is less than that. So that means I can write a less than or equal to, and cancel the pi with the div of the Li. So that means it's just a minus e left over plus n div z. And well, if I have an estimate already in that direction, I can skip the minus e altogether. Right? It's less than or equal to n div z. So that means that divisor d prime is less than or equal to n div z. Now the point is just as I said. So by this homework, we know that for this divisor n div z, this inequality holds. Actually with equality. But it holds with, as it stands, it holds there. And now we have another divisor, which is d prime. Not div. We have another divisor d prime that is less than or equal to n div z. So that means by the second remark, it will hold for that as well. And then d is linear equivalent to d prime, so it will hold for that as well. And that means this inequality that we have here also holds for this arbitrary divisor that we started out with. Oops. So now, again by the homework, export. We know that the inequality, which I raised, I guess, so the inequality star holds for n times div z. That means now, as we've just seen, it holds for d prime, which is less than or equal to n div z. And that means it holds for d, which is linearly equivalent to d prime. And that was the statement here. So that means that if we summarize everything we've done so far, that this number L of d, it does depend not only on the degree, so it will depend in general on the position of the points, but we have bounds by the degree in both directions. Okay? So summarizing. We have seen all e with deg d greater or equal to 0, we have that L of d can be bounded between in both directions by deg d plus 1 on the one side, and on the other side by deg d plus 1 minus g on the other side, where this d is the genus depending only on the curve. So this is in our case d minus 1 choose 2. And there's no hope to get anything better in terms of just the degree of the divisor, right? Because we had seen that. So this is the best constant we can get here. So there will be a divisor where this one is achieved. And so in general, L of d depends also on the position of the point in D. So that's what we got so far. So meaning that there will be no better bound of this number or this number if we just use the degree of D. And just take D. Right. Right. So there are questions there? So that might seem like the end of the story, but actually it's not quite, because there's, as I said, not just Riemann's theorem, but also a Riemann-Roch theorem, which can make this into an equality. However, also without really knowing the exact position of the points, but we can identify like the term that misses to make this into an equality as in fact another number L of something, where to just take a different divisor. However, this is the way to make this into an equality by adding some L of something for another divisor. And that will lead to the so-called Riemann-Roch theorem, which we do next time. But we can already start with the construction needed for that, namely the construction of this other divisor that will then occur there. And for that one needs something that is called a canonical divisor. And this is what we need for this. Following definition. Let me first write it down and then I'll say something about this. So we define as something called a canonical divisor. Namely, so let F be a projective curve. Then say of degree D, we'll need that. Then for any line L, the divisor class, and we denote this by KF, so that I guess the standard notation that, so K is as a letter for the canonical divisor, and that is defined to be D minus 3 times the divisor of the line. And this is always essentially considered as an element of pig F and not of div F. It's called canonical divisor class. Of F. So before there's any questions about that, so 2 remarks about that. So first of all, that does seem to depend on a line, but actually it doesn't if we consider it as a divisor class. Because if I have a different line L prime, then L prime over L is a rational function. So that means it gives, if we add this D minus 3 times div L prime over L to that to get the other one, we'll get the same divisor class. And so that means the class actually is independent of L. Note, this is independent of L, namely if L prime is any other line, then we can add D minus 3 times the divisor of L prime over L to that to get the other, which is defined in terms of L prime. And hence that, so that we do have this choice of a line L there is not an unnatural thing. So essentially the choice drops out. So I could just write Z, for example, the coordinate Z, a fair choice. So if L prime is any other line, then we'll get that D minus 3 times div L prime is D minus 3 div L plus D minus 3 div L over L prime, and that is the divisor of a rational function. So this will be 0 in pig F. And so that means in pig F as a class, it's that is equivalent to D minus 3 div L. So the choice of line doesn't matter. But of course, I mean, if I call it canonical, so canonical sort of means it's a naturally defined thing without any choices. And even if it doesn't depend on the choice of L, one might clearly ask why we put this factor of D minus 3 there, right? That it looks a bit random, and we could equally, it seems equally justified to put a D there or no factor or anything else. And there is actually a reason for that, and I can just say this in a remark in the last 5 minutes, that goes a bit beyond this class. Namely, we had considered, or I had talked about already in the last lecture when we did this analytic treatment of curves, about differential forms on curves. So we did this only in the analytic setting, where we said that we can consider expressions in the term of the form f times dg, like a formal differential. And there we considered, for example, residues of that thing in the analytic setting. Actually, there is a way to define differentials. Also, maybe you've seen this already in algebraic settings in some points, so in a purely algebraic way, in the same way as like polynomials or differentials of polynomials can be defined entirely algebraically. So there's formal differentiation of polynomials and hence also of rational functions. So there's also entirely algebraic ways to introduce differentials on curves. So that's not part of this class. There's just a way to do that. And such differentials, as one might expect, in the same way as differentials in the analytic setting had residues, so like poles and coefficients in front of them, these differentials in the algebraic setting also have orders of vanishing. So you might assign these multiplicities also to differentials. You can check where they vanish, where they might have poles, if you have rational differentials. And that means you can take differential forms and also take their differentials and take differential forms and take their divisors, namely by adding all the points and taking their multiplicities. And if you do that, what you get is a divisor class. You could check that any two differential forms would give you the same divisor, and the resulting thing is called the canonical divisor class. And it's then just a computation that the result that you get will give you this divisor here. And that I want to skip all here, and so just write down as a remark. So why these canonical divisors are in fact canonical in the sense that they are naturally defined. Maybe there's a way to introduce differentials. So these are things like of the form alpha or omega, as we called them, like f times dg. So formal differentials on algebraic curves. And associate multiplicities and divisors to them. What it means for a differential of that form, alpha of this type, there is a divisor with alpha in the same way as before, and then you sum over all the points and check what the zero and pole is of this differential form at this point. And one can check that any two differentials or differential forms, the same differentials, give rise in this way to the same divisor class. And then usually the canonical divisor class is defined to be the class of any divisor of a differential. And that is clearly then canonical. So if we do this construction of differential forms on a curve, that doesn't involve any choices. It's just formal differentiation of functions on these curves. And if we know also that it doesn't depend on the particular differential chosen, then this is an entirely natural definition. And if we did that for, let's say, for which there's no time here, one could do this in algebraic geometry class, but not here, then if you do this and compute this, the result will be that this is the divisor that comes out of that. And that's why we take the shortcut and just define canonical divisors like that. To do that, one can show that the divisor class of such a differential on a plane curve of degree d is d minus 3 times the class of a line. And that's why it is actual canonical. And we'll see that in our statement and proof of this Riemann-Roch theorem, it will play a particular role where the number d minus 3 is really important, and that's where it comes from. Of this divisor class is d minus 3 times the divisor of a line as we just defined it here. So that's why we essentially take this as a cheating definition, sort of. I mean, it's an exact definition, but to call it canonical is a bit cheated. Yeah, so that is, I think the time is up. So then we'll stop here for today. And as announced then, so next time we'll see that using this canonical divisor or combining it with the original, we can actually add a term L of something involving the canonical divisor to this thing so that we can get an exact equality from that next time. Yeah, so then I guess we'll stop for today.